Hello, it's another Chilled Math stream. Just me on this one. I don't have Matt Parker on this stream. That would be amazing. Morning, Matt Nash. Hello, Herb. This is the one where I just slowly learn some number theory. Like the weekday show where sometimes I talk to Matt Parker about leap years. It's a weird job. I'm very excited. I got to meet Matt Parker on Zoom. Life goal. How's everyone doing? You all right? Twitch is being weird to me. Yeah, cool. Okay, yeah, it was a fun crossover in a way, in the sense of we got Matt Parker to do a video that kind of Matt Parker had already done sort of 8 years ago, but with live interaction and in the Maths Club style, where people interrupt a lot and talk things through, and we go off on tangents. And also, I was there. It was a whole thing. In terms of preparation for me, I did so much preparation on continued fractions, and then we didn't use any of it because it didn't go in that direction. I think if you watch it, there's a moment where I propose continued fractions as the next thing we might talk about. There's this lovely moment where I'm like, I think you could justify this with continued fractions. And then Matt Parker says some stuff about continued fractions being a very sort of fad from 100 years ago. And it's clear to me at that point that I am not going to be able to talk about continued fractions for very long. They're a fad. We're not going to do them for very long. And all of the bits and bobs that I'd found out about continued fractions or read up in advance went in the further reading. But this is good news. It means that if you're keen, there's further reading notes. It makes it easier to write the further reading notes if we don't do everything. But this happens quite a lot. It's one of the reasons the further reading notes exist. That we'll plan something, and then the actual episode happens, and because of all the live interaction, all the stuff that we want to do, it ends up in a different direction. Hi, Mary. Oh, thanks. Yeah. I had a birthday. Best birthday card, probably this one, all the waves. It's from the V&A. Well, I mean, it's from my grandparents, but it's also from the V&A. Best birthday card because big fan of waves. Right. Imagine says we can do that now if you want. What do I want to do? There's continued fractions in these lecture notes if we get far enough. This is the weird kind of crossover between all the bits of maths in my life at the moment. So I think my plan for this is to do a bit more of what we've been doing. But I know we've been doing the same 10 pages of lecture notes for about a month on this stream. And that's probably a bit wearing. So, for your interest and because it's more fun, I think I'm going to look at the next section of these number theory notes. There's some cool stuff in there. Whereas, really, if I was a very good student and if I was learning this properly, I think what I would do next is go into this sort of the depths of pages 26, 27, 28 to work out this thing about the missing ingredient that I don't really understand from these notes at the moment is the relationship between x squared plus y squared and n squared plus 1. There's some relationship there to do with being properly represented by a form with first term n. That I don't quite understand that. But you watching me not quite understand that for another 2 hours is probably not a good use of your Sunday afternoon. So I think we might push on. Who have we got then? I've got Mouse Nash, Murray. Twitch says 4. I never really know if I trust that number or not. Maybe the 4 includes me. Team. Okay, I've got another list of page numbers. I want to do the thing where I look at each page. There's only 10 pages in this section, and it does lots of stuff. It's unreasonably cool. Switch, but not to. Yes, good. this thing switches documents in quite a scary way. If I do this wrong, I'll just accidentally show you like somebody's work I'm marking. I have so much marking this weekend. This might be a short stream because it's the end of term and I've got so much marking and report writing to get done by the end of the weekend. Okay. So we have done a few things on prime numbers, and this section is about the distribution of prime numbers. Something that I know you've got some intuition for. You know that there are lots of small prime numbers, there are infinitely many prime numbers, so there must be quite a lot of large prime numbers, but it feels like they get further apart. And I'm hoping that this section of the number theory notes can help me understand more precisely how that works. This is the this is the end of the Oxford term before the Easter holidays. The Oxford terms have a 6-week holiday for Easter, which is ridiculous in some ways, but don't tell the students I told them that. Don't tell the students I said that because they love their 6-week holiday over Easter. It's so much holiday. Oxford's got really short terms, 8 weeks of my tutorials. So somehow it's the end of term next week. I need to write my reports now. Ugh, 8 weeks. Yeah, 6 weeks for 6 weeks off for Easter. I think I counted them. Let me see. Let me fact check myself. Yeah, because I saw my students. I'm seeing my students this week coming, and then they all go home. So they're away. They're not in Oxford the 11th of March, and then I don't see them again until the 22nd of April. So they get 1, 2, 3, 4, 5. Is that 5 weeks off? 1, 2, 3. No, wait. 1, 2, 3, 4, 5, 6. Week commencing 11th of March, 18th of March, 25th of March, 1st of April, 8th of April, 15th of April. I didn't see them for any of those 6 weeks in a row. And then they come back and they have another 8-week term with exams in. Yeah, it's not the same at every university in this country or on this planet, but boy, is that how it's done at Oxford. Okay, I would desperately like to generalise these facts. There's a theorem, right? Yeah, here's Dirichlet's theorem down just off the bottom of the screen. Obviously, so these are two cases, right? Primes that are 1 mod 4, primes that are 3 mod 4, and then not pictured here, there is 1 prime congruent to 2 mod 4, and there are no primes congruent to 0 mod 4. So proof here, see even numbers, which is a separate thing we learn about, and then this is like C multiples of 4. There we go, cool, I've completed the pattern for you, there we go. It's in a weird order, but 0, 1, 2, 3. Mountain Ash is excited for 6 weeks off. Did you not know about the term dates thing? 8 weeks. Oh, it's several weeks at Christmas time as well. What is 0? What do you mean? What is? Oh, do you want me to say 4 mod 4? Is that happier? Is that what you need? Good. Okay. We can't show there are infinite many 2. What happens? Yeah. Okay. Good. Are there infinite many primes congruent to A mod n where their highest common factor is 1? So you think probably yes. Is this a real theorem? All primes, things in favour, all primes lie in. Oh gosh, can I remember what that is? Residue. Oh, that's how many residue classes there are coprime to n. Finitely many exceptions. There's no obvious reason why one class should be more popular than another. Yeah, right. Hey, Neutrino, you're right. Okay. This is Dirichlet's theorem. Ooh. Oh, so this might be exciting. It primes in arithmetic progressions? That's not the same thing as saying arithmetic progressions in the primes, which is Green Tau result, right? From a few years ago. The other way around is harder. This is Dirichlet's theorem on primes in arithmetic progressions, that way around. Okay, infinitely many primes congruent to A mod n. Okay, I always love a slogan. If it's not obvious why there aren't infinitely many, then there are. Are there infinitely many primes that are 3 mod 6? No, obviously not. Are there infinitely many primes that are 5 mod 6? Yes, says Dirichlet. Okay. Proof is not in this course. Small hint of an idea of a proof. That's why you come to this live stream, right? You come to this live stream for a small hint of an idea of a proof. There are other live streams out there where you can get an idea of a proof. So maybe not live, but 3 Blue 1 Brown does really good videos on the idea of the proof. And there are really good channels that give you the actual proof, where you can actually sort of learn perhaps university level maths, I think. But you come to this live stream for a small hint of an idea of a proof. That's the content we cover. Just a little bit of an idea. Okay. Yep, this is a good strategy. Proof by contradiction. Do something clever to find a member with a prime factor that also has this property. Member with a prime factor that also. Check that this prime is not on the original list. Oh yeah, okay. So this is the classic proof. Something clever. So this is like where you multiply them all, and then times by 4, and then subtract 1 or something. And that's part of a proof that I've seen that in a proof that there are infinitely many that are 3 mod 4, which I think we did. It's on a problem sheet. That's the one on a problem sheet that we did. Oh goodness, about a month ago. Okay. I come to this stream to be confused. I've just seen that. How do I edit command? How do I make that like a quote? How do I add quote? Wait, let me add quotes. Oh no, I have to log in and stuff. I've no idea how to do that. Right, cool, we'll drop that. Okay, so we're going to look at the reciprocals of primes instead. We know that 1 over n diverges, but does 1 over p. And the proposition here is that yes, it does, because it's bigger than log x minus a half, or whatever. Okay. And you can actually show that it is the sum of the 1 over the primes up to x. Primes is log x plus c plus o, and then this this notation here means that the remainder is of the order, so it means the size of the leftover bit is this size, 1 over log x. The big O thing has a technical notation. It's more of an equivalence relation than a function, but it's terrible notation for an equivalence relation to say that these things are equal up to a member of something that is that size for sufficiently large x. Big O means it's that size or smaller. Yeah. That's a remark, but not an important one. This is trying to assert that people have got some idea of how large the difference might be. You see a lot of results like this, right, where you're interested in the kind of asymptotic growth of something or the asymptotic behavior. How many primes are there less than x is a really hard question. Roughly how many primes are there less than x is much easier, because the first question you're going to have to say something like 1,000,003. The second question you can say about 10 to the 6. Maybe it's about x to the 6. That's not how many primes there are, but that kind of approximation. And there's ways using limits to make these ideas more precise that I'm not going to tell you about now. Okay. Can we prove this? Oh yeah, so hopefully this is a proof of proposition 44, which I'm going to skim read now. Oh look, it's got a little picture of 1 over x. Stirling's formula, yeah, so Stirling's formula gives you a rule about how large n factorial is for large n. And it says that n factorial is asymptotically, which people do this kind of tilde symbol, which is like 1/2 of a roughly equals to sign. And then the way I remember this is it's like n to the n, e to the minus n, surprise factor of 2 pi, root 2 pi n, which is quite a cool formula. it's giving me all these vibes of binomial distribution and normal Gaussian curves, and that's exactly what's going on. Stirling's formula is so good. It's not telling you that these things are equal, or even that they're particularly close together as numbers. The difference, the kind of percentage difference, goes to 0. Yeah, it's everything all at once. It's got a factor of 2 pi. That's great. Have I remembered that right? I think I have. Mountain Ash just learned Stirling's formula. They'll correct me if I've missed a factor of like, I don't know, what would I miss? A factor of like gamma? What other numbers are there? We've already got e and pi in there. It's all-star equation. Yeah, it's bond. Good. Okay, I've remembered Stirling's formula. We're going to move on to this proof. Idea. Oh, we get a full idea in here of a proof of this proposition. Several steps removed from proving the thing. But this is good because this is something I cared about on this show. We were doing multi-perfect numbers. No, what were we doing? We've cared about this before. Yeah, so we cared about, the thing we actually cared about was more like this, wasn't it? We were multiplying together some prime numbers and looking at the sum of the factors. And then the sum of the factors is something like, there was a link. There was a big product. People in chat were trying to work out if you can make the abundance as large as you like. I suppose we were looking for multi-perfect numbers with large ratios between their sum of factors and the number itself. And if this thing were bounded, then there'd be a limit to how perfect your number could be. That was fun. Oh, so this sum notation where they've written, there's a lot going on here, isn't there? It's sort of the sum over p less than or equal to x, where I guess maybe they should also say that p is prime. That's a sort of that's another condition. We're only looking at the primes up to there. So really, I think you should have some p is prime. Fair warning, I've also seen people do things like define the set A to be the set of p less than or equal to x such that p is prime, and then write their sum. So I guess that's a depends on x, so maybe I'll write a subscript x, and then to write their sum like this with the set underneath as the kind of subscript to sum over the things in this set. Sometimes the things you're summing over don't just lie in the kind of index list 1 to n. It's a bit like how, oh gosh, let's see if this lands. It's a bit like how in Python, you don't have to set up a variable like I, set I is 0, read off the first element of your list or whatever, and then increment it I is 1 and read off the next one. You can do for word in words to say for this thing in all of them. Here's the set, go through everything in the set. Obviously you might want to increment some variable or something, but just for word in words, go through all of them. Is that going to land? Python? I'm trying to learn Python, but I've been trying to learn Python for years and I have gotten nowhere. Okay. Good. Okay. So, it's kind of the Wild West in a way. The job with this sort of math communication or writing lecture notes is to write down some sort of sum and indicate what you're summing over. Yeah, there's a Python thing like that. Okay, good. Okay, what's this sum then? So we're going to look at the logarithm of this product for all the primes. So this is the sort of thing we looked at with the... Oh, it's not quite the sort of thing. It's really reminding me of those multi-perfect numbers. Let's try and get that out of my system. So with the multi-perfect numbers, we were looking at things like this. where you had, I guess that sum doesn't go on forever for the multi-perfect numbers. If you had a prime factor p, we'd say, aha, you can have a prime factor p. These are the factors of p to the n. What am I saying? If you've got a factor of p to the n, then all of the factors of your numbers might be multiples of p, or they might not. They might be multiples of p squared, or anything up to p to the n. But that's it. Like, you know, if you're a multiple of 25, but not 125, then your factors might be a multiple of 25, but not 125, or equally 5, or just not multiples of 5. So we saw things like this, and then we multiplied those across your different prime factors. That was our multi-perfect thing. And that's nice because can't spell perfect. Irony. That was nice because these things are geometric progressions. I'm getting distracted. Dodgy Python code. Yes, now that we've done the crossover. We can say dodgy Python code. Okay. Look at this. So this includes loads of stuff, including, because if you were going to multiply out this product, so this is a huge product of things, not to be confused with the sum, big sigma, product big pi, S and P, sum and product. That includes 1 at the front, and then this product has got all of the 1 over p's. I'm confused, it's also got a log, right? Maybe they don't really mean the log yet. So this includes this inside the log. Inside the log. Okay, so that's what this is, which is bigger than or equal to, ooh. It's not as big as that. What's going on here? No, it's bigger than that. It's bigger than. So, okay. This product is the thing inside here by geometric progression stuff. This sum here, so I guess the same sort of idea, right? That 1 over n has got some, if n's got some prime factors and powers of primes in its factorization, then that term 1 over n will appear, the prime numbers are smaller than n. Okay, this sum is small because it's just some of the things that you can make by multiplying out these brackets. We've got relatively small primes, but that's enough to make anything up to n. If n is prime, we've got that prime in there. If n is made of smaller primes to some powers, then we've got those in there as well, because they'll be small primes, and we've got all their powers. So we can make n, or really I suppose I mean 1 over n, by multiplying out these brackets, plus loads of other stuff. I guess we're going to make some of the things that are like 1 over n, but larger values of n, but we're not going to make all of them. Some of them. Which is good news, because it means this thing's going to be finite. But anyway, it's bigger than this thing, which you can approximate with an integral. I've seen this trick before for proving that 1 over n diverges. It's kind of snazzy. You take the 1 over x curve, and you pretend that you're integrating it. You draw these rectangles, but the rectangles overshoot the curve. So when you try to integrate it, on the one hand, you get log of x, or log of x or something. On the other hand, you get some rectangles. Hi, Vampy, welcome to chat. Good to see you. I don't get it either. This is a stream where I don't know what's going on, you don't know what's going on, and between us, we're trying to understand some maths. Yeah, there's several steps here, right? There's really several steps. Do we have a loading emote? There's got to be like a thinking. Not the best way of doing that proof. Wait, which proof? The proof that sum of 1 over n is bigger than log x? Or do you mean the whole thing? So sum 1 over... Okay, now I'm going to focus on this bit. This is going to take me ages. Yeah, okay. Oh, it's not the best way of doing the proof that it diverges. No. The proof that it diverges, I should do the group the terms together. You're right, Mountain Ash. This proof has the advantage of telling you how fast it diverges, or giving you a lower bound for how fast it diverges. Okay, I think I believe this. So this says that this product's really large. Do I want this to be large? I don't know. It's large because it includes loads of other stuff, right? It includes loads of stuff, including numbers bigger than n. Let's set the logarithm, and then what? Just hope that this shows that remaining terms. Okay, not convinced that this is helpful yet. Let's go. Because 32 looks like part of the proof, but it's in fact a page number. Have I bitten off more than I can chew here? Let's find out. So some logarithm facts are happening. If you do the log of this. So for each prime, no. Yep, for each prime, this is log of a big product. So we're looking at log of each of the terms. We're going to be adding these, I suppose. And there's some bounding going on to mess around with the logarithm. Expand the logarithm. This is a Taylor series for the logarithm, right? Am I completely off base? No, that's a Taylor series for the logarithm. Okay, so this is just cancelling out the 1 over p. And then this thing is another geometric sequence, which is this. So that's a bound to say. Okay, so we've got this crazy product over the primes. Over, I'm going to call them small primes. And we're saying that log of this thing is small. It's smaller than the sum of 1 over 2p, p minus 1. Okay, that's telling me it's small, but on the other hand, I think we've also been told that this product over the small primes is larger than log x. So I'm a bit confused about where this is going to go. I'm a bit confused about where this is going to go, looking over there. Yeah, okay, so this sum is really small. Oh, thanks for the follow, VampySim. VampyC, sorry. One more time, clean take. Thanks for the follow, VampyC. We're trying to get to 14 squared. And I think the sound played that time because I worked out how to turn that back on. Okay, horrible sum. Oh, but this sum includes the sum of 1 over p. And that's right, okay. Okay, so I missed out this sum of 1 over p, which is very much the thing that I wanted. Back a mode. Let's put this into my kind of understanding scribble in the corner. It's not rigorous, it's not good. I've missed this minus 1 over p here. This says that this, what do I want? Oh, I can't really do the product anymore, can I? Minus the sum of the 1 over the primes is small. This thing, with this thing is less than a half. It's going to be on the next page. This is just a sort of telescoping sum proof. So it's less than half. But this product over the small primes thing is big, so it's going to be. Okay, so this is going to go onto the. This is going to turn up on the other side. This minus 1 over p. I'm scribbling on a PDF using my Remarkable tablet. Not sponsored. It's one of those ones that's a bit like paper, and you draw on it with a pen, and it's doing a screen connection to my computer so that I can rebroadcast it. I get a huge number of adverts for these things. Just to be really clear, this is not an advert for Remarkable. The stream is not sponsored by Remarkable. If anybody from Remarkable is watching, then I would accept sponsorship. Or equally, if you could just stop sending me the adverts for them. I've got one now. I'm not going to get a second one. I've got one. That's enough adverts for me. That might save you some money too, Remarkable people. Right, good. It just lets me draw on things. Its usefulness really depends on how many PDFs you have in your life. If you have a lot of PDFs in your life, then having a device that basically just does PDFs. I know it like technically it does ebooks or whatever, but a device that basically just does PDFs and lets you draw on them without printing them is really good. If your life is like not just PDFs, then I don't know, something else. Yeah, so this app is this app is literally just me pointing and drawing at the same time. The app comes with the thing. For other things, I've got actual graphics tablets. Feels mean calling them actual graphics tablets. The work stream, the professional stream has like a graphics tablet and an online whiteboard, Miro. But for this, I've got this lying around. Yeah, I have got hundreds of PDFs on this thing. Love PDFs. Right. Okay, so this says the sum is small, and I believe this is sort of telescoping sum. If you haven't seen this before, it is fantastic. I'm skipping it because I've seen this proof before. The thing that you're trying to do here is this sum. Do I mean this? Yeah, I do. Which is a surprisingly small number. And it's finite and rational. All the good things. Right, so I missed the -1 over p, but there it is, to great effect. And so this says that log of all of these things, that is log of the product. We sort of convinced ourselves that this was large. Was that one large? But this is small. If you subtract off this stuff, you get something very small, smaller than 1/2. So what's going on here? Then log x minus the sum of 1 over p. It's less than 1/2. Okay. Does that make sense to me? We've replaced, yeah, okay. We know that this thing is large, so replace it with this smaller thing, log x. And rearrange this neatly. Okay, so there's this thing about the way it moves around, terms change sides. Oh my goodness. Not sure I've got the endurance to trace all that in my head, but crikey. Right, let's have another go then. Got a follow from VampC, whose only chat message at the moment is I don't get it, and I think I want to try once more now that I feel like I understand it a bit better. So we're looking at the sum of 1 over p for small prime numbers, only the primes up to x, and we're trying to prove that that's larger than log x minus 1/2, which is a tall order. Our strategy is going to be to prove that, well, so prove something slightly different, to prove that log x minus the sum of 1 over p for the small primes, to prove that that is smaller than or equal to 1/2. That will be enough because then that rearranges to the thing that we want. This thing on the left, we're going to get there by considering log of some really complicated product. The product means you multiply together all these terms. I guess each term here is not each term in that product, when you do the logarithm, it's not that different from 1 over p. There's a kind of very small difference between that and 1 over p. Is that true? Yes, I think we're saying that these are small numbers down here. They sum to something less than 1/2. So small difference between 1 over p and this logarithm, which you believe, if you believe it at all, you believe it because of the Taylor series and this geometric thing that's going on, where we've taken a Taylor series. We've done the thing where you take a Taylor series and you replace the coefficients with different numbers so that it becomes a geometric progression, and then it sums up like a geometric progression. I'm smiling because I've realised that those steps are something that I've done in a math question before, where you take an expansion, you replace the numbers, and you sum it like a geometric progression. Okay. So if you believe that these things, are similar at all, it's because you've done a sort of Taylor series approximation. Maybe we could just calculate some of them. Let's say that 1 minus 1 over 7 6/7 log 7/6. Log 7/6 is not that different from 1 over 7 is the thing. They both sound pretty close to 0, so sure, that's not the proof, but yeah, sure, those things both sound quite small. Yeah, that's basically it, right? These things are both pretty small. How far apart can they really be? Not a real proof. Okay, this is good because now we've got some logarithms, and our plan to sum over the primes. Instead of summing over the primes, I'd much rather sum these logarithm things, because the sum of some logarithms is the same thing as log of the product. That is this thing used to the kind of logical extreme where you've got just loads of things. Okay, so is there a lesson for me here? If I see a sum, I should be trying to compare it to a logarithm of something, don't really mind what, so that I can combine them together into log of the product and argue about the product instead. That doesn't feel like a lesson, but it's what's happening here. Okay, so then up here again, we've got this product of what this thing actually is. We looked at its expansion, and we saw that as a consequence, you've got this product with, so let me try and write out some of this. It's 1 plus a half plus a quarter, that's the first prime, times 1 plus a third plus 1/9 plus 1 over 27, and so on. And that's nice because it's got some 2s and 3s in it. And already I can see when you multiply this out, it's going to give you things like 1 over 4 from this 1 times this 1/4. It's going to give you things like 1 over 6 from this 1 over 2 times 1 over 3. It would give you 1 over 5 if we had the prime 5 in here as well. We haven't got 1 over 5 yet, have we? But if I put in another prime, well, now it will make things like 1 over 5. And in fact, it will make 1 over anything up to 5. It's not a very strong claim, but yeah, okay, you can make the number 2, 3, 4, just, and 5. I guess the claim is that if you put in the prime 7, you can make everything up to 7. You make 1 over everything up to 7, and so on. Any whole number. So if you forget the reciprocals for a moment, because I don't want to say 1 over lots of times, you're looking for 1 over n. I just said it. Okay, you're looking for the number n to appear as the product of some of these terms. That's not going to happen for any n, right? I can't see 1 over 11 coming out of this mix. But if you really limit the thing we're looking for, so that you can get up to, as long as you've got all the primes below a certain point, then you can make everything up to the next prime. So here I can make 1 over 6. I can't make 1 over 7. I would need the bracket with all the 7s in it to make 1 over 7. But once I've got the 1 over 7, I can make everything up to the next prime. I can make 1 over 8 because it's in here. Its factors are just 2s. I can make 1 over 9 because it's here. 1 times 1 over 9 times 1 times 1. I can make 10 because I've got a 2 and a 5 now. I can't make 11. But you can factorise all the numbers up to the next prime just fine, because their prime factors are smaller than the next prime. That lets you make lots of numbers up to, well, we're considering numbers up to some point x, where you've got the primes less than x, so you can make things that are smaller than x. You might not be able to make things bigger than x because, what about the next prime number? You're not going to make that by multiplying together smaller primes. That's not how primes work. It is just like the sum of factors, except with 1 overs everywhere. Okay, sure, sorry. Okay, you cannot make pi. You cannot make the square root of -1. You can make reciprocals of whole numbers. up to x. Thanks for making me say it out loud though, because I was talking like you could only get up to this prime and you can actually get all the way up to the next prime. Plus, for free, you make lots of extra junk. So with these ones on the board, I can't make 1 over 11, but I can make 1 over 12, and 1 over 18, and also 1 over 243. I put in really lots of these. This dot 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 is hiding lots of prime powers. Lots of these things. So much so that this product must be kind of large. Oh, now it feels weird that it converges, right? It does converge because this is finitely many terms in this product. There are only finitely many numbers below x, let alone finitely many primes. And each one of these infinite sums converges by the magic of geometric progressions. So now it feels weird that you're making lots of these numbers, and I know this series is dangerous. Ooh, yeah, okay, so this thing is finite, but it's bigger than log x. That's delicate. There's a result hiding in here to say, which numbers have you made? And you've made all of the numbers 1 over. You've made 1 over anything whose prime factors are small. So anything with prime factors 2, 3, 5, or 7, that appears in this product. And their reciprocals sum to a finite amount by geometric progressions. So that makes them different from natural numbers, the whole set of natural numbers, and we're going to see different from the set of prime numbers. These are called smooth. Are they called P smooth? Yes, it's P smooth. P smooth numbers are ones where the factors are just 2, 3, 5, or 7. In general, there might be some set P of your favourite primes. For me, I'm looking at small primes 2, 3, 5, and 7. P smooth numbers are ones that only have factors in that set. And I think this geometric progression stuff is to say, if you look at the P smooth numbers, their reciprocals converge and they cover everything up to, if you've got all the primes below x, then it covers everything up to x because of factorization of all of those numbers. So maybe a bit of language on here is helpful. Let me check I've done P smooth correctly. Yeah, okay. Oh, so they're called N smooth. I've used a general definition with a set, but I should be using like an N smooth. Okay. So people call these 7 smooth numbers. And in general, going up to a number n, called the N smooth numbers. That bit is foreshadowing for next week's online maths club. The professional stream is doing smooth numbers quite soon. Okay. Spoilers. Not spoilers, foreshadowing. It's different. Okay, this is really cool. So you've made loads of these things. So this thing is large, because it's really large, and really similar. So this is really large, and its logarithm is really similar to the sum of 1 over p. So that means that 1 over p is really large. The sum of 1 over p is really large. It's like the logarithm of this. It's like log x. Fast, slow, fast. You read it quickly for the first time, doesn't make any sense. You read it slowly until you kind of appreciate how the small moving cogs fit together and how they work, and then you try and do it fast. Because fast is how it sticks in your memory at the end. So sum of 1 over p is large because each 1 over p is similar to this very particular logarithm via Taylor series. Summing those is like summing the logarithms, which is like taking the product of x smooth numbers, which includes everything up to x. That sum is large, it's like log x. So the logarithm of that is like log x, which is the sum of 1 over p. The difference of 1/2, which is not important, comes from the difference between 1 over p and that particular logarithm thing. I don't know how you'd invent this proof. I don't know where you'd get the idea of thinking about this. This idea is still amazing, and sort of alien. I think I'm getting there. Like I could maybe recreate this if I had to on a blank bit of paper. Ugh. I'd have to remember how Taylor series for logarithms work. Okay, we're going to move on. We've got some idea about the sum of 1 over p, which is more than I had when I started this stream, so that's pretty good for going for 45 minutes. Stupid corollary, there are infinitely many primes. Because if there were only finitely many, this sum would be finite after all. The sum would be finite. The sum would be bounded, sorry, by the sum of all of the 1 over p's. Right, so what are we doing? Dirichlet's theorem was looking at a particular. Let's look at this restricted group. Restricted group. Ooh, and 1 over p to the s. Sounds like a zeta function thing. Tends to infinity, so that also grows with x as s tends to 1 from above. Which means that then there are infinitely many of those as well. Why do you need s tends to 1 from above? Isn't it okay? Oh, maybe it's only true when s tends to 1 from above. That is mad. That's a weird combination of limits and sums, and I don't know about that. Okay, this proof is not in the course, but I like the idea that you have to prove it for s not equal to 1, slightly larger than 1, and then take the limit. Yeah, how do people think of these things? I think they try lots of things. I think the answer is they try lots of things. Possibly on a kind of theme. So maybe you would try lots of different sorts of logarithm or something. I don't know. Lots of things with, I guess, lots of things that try and relate the 1 over p to something you know about, like 1 over n. To say, once you've got the 1 over p's, okay, if you multiply those together with powers, then you can make things that look like 1 over n, and that's a comparison. And then try and see where you can go from that comparison. I'm not saying we could rebuild it from just the idea that 1 over p squared builds 1 over n. I don't know about that. But maybe that's the kind of germ of the idea, that you can use, there's a comparison between 1 over primes and 1 over n. That link is factorization. That link is that if you take some small primes, you can build some small numbers. But you need some sort of link. I don't know who proved this and how long it took them, but mad. Not mad. Okay. One needs a way to pick out primes in this congruence class. I do this using Dirichlet characters. What is going on here? We shall not say more about this. Okay, cool. What is going on here? We know that all but finitely many primes lie in the residue classes that are coprime to n. Are they evenly distributed? So if we think they each have infinitely many in, but then to see, right, the number of primes less than x that are in a particular congruence class. So you might say, are there more that are 1 mod 4 or 3 mod 4? I've heard about that. That's called the prime race, I think. Let's see if it's just down the page. Okay, I can't see it on the page, so I'm going to write a little bit about prime race, which I think is a thing. Prime number race. Yeah, it's halfway down the Wikipedia page on this, which says that no. Yeah, let's put this on screen. Wikipedia and Control F, my two greatest research techniques. So this is talking about primes that are 1 more than a multiple of 4, and then also the number of primes that are 3 more than a multiple of 4. Empirically, the ones that are 3 mod 4 are more numerous and are ahead. So, but the first reversal occurs at 26,861. So here's the function. How many primes are there of the form 3 mod 4 minus how many primes are there of the form 1 mod 4 up to a particular number n. So you get to 5,000 and you find, the primes that are 3 mod 4 are ahead only by 10, but they're ahead. Again, they're all the ones that are 3 more than a multiple of 4 and they're slightly more. And it comes down, it gets very close, but the 3 mod 4 ones are still ahead. Up here, you get to about 16,000 and it's about 20 or 30 more. But then just around here, where is this? So it's 26,000 or something. This sum goes negative. What did they say? 26,861. I cannot see that in the picture, but hey, it goes negative. So this is a sign change, and Littlewood proves that there are infinitely many sign changes. So the lead in the race switches back and forward infinitely many times. The fact that 3 falls ahead most of the time is called Chebyshev's bias, which we could link to, I guess. That sounds open. Right, good. Okay. Whoop. Yeah, it goes negative, and then it swaps backwards and forwards, and Hardy Littlewood kind of thing. I've said Hardy Littlewood, but Wikipedia has that's my bias because Wikipedia just says Littlewood. Infinitely many swaps. But that's not quite the thing on the page here, which is just asking if they. Oh, might be. There's infinitely many of each by the Dirichlet theorem. So what's going on? What's the Elliott-Hallström conjecture? These sets all have approximately the same size. What is going on here? Excuse me. Halberstam conjecture. Can I have a Math World page? No, I'm going to have to settle for another Wikipedia page. What is this? Let's have a quick look. Conjecture about the distribution of prime numbers in arithmetic progressions. Ooh, that was weird. Sieve theory. What? What? Oh no, define the error function like this. Oh no. There exists a constant such that it's like this? There's a bound on how large that is for the sum of... I'm not going to read this now. Okay, good. Right. Bye. Right. Okay, moving on. That looks very exciting. Ooh. Pi of x counts the primes less than x. And there's an example sheet question to show that it's more than log x over 2 log x. Just counting them. And here's an Erdős proof that there is a constant c bigger than 0 such that it's bigger than log x, so without the dividing by log x. I think I remember looking at example sheet 1. So this is the problem sheets in this course. Let's have a quick look. I want to go over here. Spot on. First time. Yeah, it was this. This was really cool. We did look at this. I can tell because I've scribbled all over it. And there's a proof here. And again, it looks like consider this product in here. And how the possible factorizations work. I don't really remember how this worked, but cool. Is this log x over log 2? Log base 2x. Is that how many you've got? How many terms you've got? Oh yeah, okay, so you're trying to make different numbers. How many possibilities are there? You've got a certain number of primes and you need to actually make all of the numbers using limited toolkit of how many powers of each number you can use. This was good, I liked this a lot actually. I've put cool on the left, there we go. So you know it's good. Okay, back in. So we're going to see an idea of Erdős that makes this better. Oh, I didn't quite nail it that time. Idea of Erdős to extend this. Where are we? Still here? No, we're now over here. What is going on? Write them like this. Let's try skimming it. Possibilities for what that square bit could be. And then, so these primes only appear to powers of 0 or 1 because you've taken out the square part. So it's a slightly different bound. So then rearrange everything and count how much stuff you've got. And then you get a bound for how many primes there are. Really clever. Like it a lot. Okay, don't understand it, but I like the ideas of it. It's all similar, but we felt the proof on the example sheet was allowing a lot of space. It had some sort of looseness to it by kind of treating all primes to be. It kind of treated all sequences of powers of primes to grow at roughly the rate that two powers of 2 grow at, which is not true of most primes. So maybe we can do something better. This only allows primes to powers of 0 or 1. So I think there's a little bit more control on those prime powers. Okay, that's my intuition for why this might be a good idea, and hey, checks out, works in the end. That's really nice. Good, okay. Oh look, it's the definition of the Riemann zeta function. Average Sunday afternoon. Yep, don't understand it, but I like the ideas of it. That's what we're trying to do. We're trying to see enough number theory that we think, yeah, this is the sort of thing that I should put the time in to actually study. How's it? Have you been lurking in chat just waiting for the Riemann hypothesis? It's a long wait. Oh my goodness, what is going to happen here? Why have they defined the Riemann zeta function? To be clear, this is a undergraduate course. No, we're going to do something with the Riemann zeta function. Maybe that's why you do number theory. So you can do stuff with the Riemann zeta function. That's probably it. Lemma. If the real part of S is bigger than 1, oh my goodness, look, complex numbers at the same time. Converges absolutely, which means that you can put mod signs on and it still converges. Mod signs on each term. Moreover, it converges uniformly on, for any delta. Oh. So it's analytic. Ooh, okay, crikey. So suddenly complex analysis and uniform convergence and absolute convergence, we have gone out of the shallows into, oh my goodness, suddenly loads of analysis. What is this? What is going on here? So looking at the absolute value, because that's what converging absolutely means. Look at power there, which is, oh my goodness. Yeah, use the fact that n is e to the log n, why not? And then that bit is e to the I theta, so it's got magnitude 1, so it's magnitude e to the sigma log n. Just n to the sigma, that makes sense to me. And then compare it to 1 to find out if it converges. Yeah. Excuse me, classic comparison test. Things converge if this thing's bigger than 1. Uniformly. Oh, I didn't know this fact. I didn't know this. Huh, I'm going to have to think about that afterwards. I don't think I should think about this on the stream. Yeah, so. Okay. Have I done the story about how we got Matt Parker on the stream? So you might have noticed that the professional stream this year is supported by Jane Street. And Jane Street also support Matt Parker. So Jane Street, we had some meetings with Jane Street, of course, to try and get, try and tell Jane Street about what we're up to. And Jane Street agreed to support the show financially, which we're very grateful for, but also agreed, and this was their suggestion, that they could put us in touch with Matt Parker and see if Matt Parker would be up for coming on the show. So that's a Jane Street contribution. I should probably have mentioned Jane Street a bit more on the Thursday show, but the link there is that the stream is supported by Jane Street this year, and Matt Parker is supported by Jane Street, and it was their idea. So thanks to Jane Street for not sponsoring this stream, but for sponsoring the professional stream, and getting in touch with Matt Parker. They are trading software, clever people. They do the sort of jobs that maths grads are interested in a way where you get to be clever and write code and solve problems, with the exception that unlike some maths problems that you solve, all of the Jane Street maths problems are solving problems so that you make a profit. get lots of cash. That's not always true of maths problems. Jane Street's also famous for having a lot of links to effective altruism. Not quite intentionally, as far as I know. It just happens that there's a kind of effective altruist group that latched onto Jane Street as a place to work, earn lots of money, and then give it to charity. Effective altruism is this idea about earning lots of money and giving it to charity to be the most effective, which is really popular with quite a lot of people, including, unfortunately, Sam Bankman-Fried, who's that person who did FTX. I'm probably not supposed to mention Sam Bankman-Fried on the professional stream. I don't know. They didn't put a condition on me, but it doesn't feel really that fair to be like, hey, the most famous person who worked at Jane Street, but then crucially stopped working at Jane Street before he started doing all the crimes, alleged crimes. Sam Bankman-Fried. Yeah, Mountain Ash. Impression I'll end up working with them somehow. Lots of people do, I think. I actually have no idea how many people work for them. You got a t-shirt with their logo on. The clickbait thing for me to do would be like, you know who else has got a Jane Street t-shirt and is in prison? That would be very clickbait of me and not very fair. We're very grateful for their support of Tiny Livestream. Okay, that was the weird story time about how we met Jane Street and therefore met Matt Parker. Back to the Riemann Zeta function. People want to ask story time about Jane Street. Quite a few people I knew at university went to work at Jane Street. And as far as I know, none of them have done any financial crimes. There's a maths communicator conference. It's not very big and it's not very regular. It's like every 2 years. All the people who do maths communication stuff in the UK, we have a little professional conference where people go and talk to each other about doing maths communication. Sometimes Matt Parker is there. So one of the pluses of doing maths communication in the UK is maybe sometimes you go to a conference and Matt Parker is there. One time Brady was there. Okay. This is my reminder to go and remember what convergence uniformly means. If you're watching this stream because I'm currently teaching you uniform convergence in the future, and you've dug back through the streams to find one where I was talking about uniform convergence and you found this one where I can't remember what it means, it just ignore this bit. I'm sure it'll be fine. Good. Prime numbers and zetas. Yeah, no, seriously, if you're at all interested in talking about maths in public, then the conference called Talking Maths in Public is maybe the place to be. Okay. Coming up in 2025. That's crazy, but looks like a factorization thing. Yeah, good. Is this allowed? Oh, there's a fundamental theorem of arithmetic in here. That's the factorization one, right? Yeah, factorizing thing. We've been talking about this a bit, about how you can factorize numbers together. Yeah, this product gives you all of the 1 over n to the s, but I'm sure it's a bit more technical. Oh, is it volume? Oh yeah, I know why that is. 2 secs. Better or worse? I think my microphone was just miles away. Summer of Maths Exposition. I don't think I'd do very well at it, and that would be embarrassing. Yeah, I see it happen. I like the neutrinos because my microphone was just like miles away. Sorry. Sorry if you're watching YouTube and for the last hour it's been like, this guy's microphone is nowhere near his face. It's very embarrassing. Okay. What is this? So we've got an intuitive idea, but then there's loads of maths happening? I don't know about this. I quite liked the intuitive idea. What's going on here? Oh gosh. Fixative. M is... okay. if m is bigger than this, then that prime is bigger than prime power is bigger than n. What? So the product, we're going to get this plus some other things with larger values of n. That's the thing we wanted. Oh gosh, okay, and then we're going to bound it. Let's say that's, ooh, the remainder stuff. But that stuff converges, so we're all okay. Take m to infinity to do this for all of them. So sort of swap some. It's like trying to swap some limits, isn't it? It's doing a lot of work to try and swap some limits and not worry about the leftover bits. That thing goes to 0 because sigma's bigger than 1. Okay, cool. There's some limit swapping thing to check that the leftover terms aren't going to be a problem. Okay. Oh, good luck with the chess. What's happened before? Consider moving the queen. The queen is the best piece and moves in lots of different ways. Wait, hang on. So Neutrino says, but wait, I heard that doing pure maths as a job is really hard because it's not you, but your employer who has to be passionate about maths. Oh, you see, if you want to do maths as a job, you need to find maybe the hard half of that is job. You need to find someone to pay you to do pure maths. Are we talking about research, or are we talking about like people applying maths to various problems in the real world? There's a lot of both of those things happening. If you do pure maths research, then your employer almost certainly cares about pure maths enough to employ you. Although you have to hope that they don't change their mind and decide that they would like to do history research instead. Nothing wrong with history research. Just I get nervous when universities talk about not doing pure maths research. If you want to do pure maths research somewhere else, then you have to convince them that the fundamentals are worth it. Thank you for the follow. Who was that? Oh, I missed it. It's still on screen. Can I look? How am I going to pronounce this one? Okay, that Trippica. Yeah. Thanks for the follow, that Trippica. Your follows help us reach a follower goal. And you're in chat as well. Welcome to chat. Welcome to the math stream. We're just doing some stuff with the Riemann zeta function here. We can. The rule for helping is that we can try. But you've got to describe the problem. You've got to describe what you're doing, and maybe chat is more helpful than me. People in chat here, very clever. We once managed to do an integral that someone was describing. It varies. So welcome to chat, that Trippica. I imagine that you've done something like type math into Twitch and you found us. If you can type your problem in chat, we can have a go at it. Complex numbers. Sure. What do you need to know? Can I point you to Complex Adventure? If you are you starting with complex numbers? Or starting with complex numbers, but you've seen some algebra before? I have a website for this. I'm gonna let that Trippica tell me whether it's okay. Is it like starting with complex numbers? I'm really good at starting with complex numbers. Is the later bits where it's all like roots of the Riemann zeta function. That's the bit that I find tricky. People in chat might also be thinking about how they first got to grips with complex numbers. Can you remember what it was like the first time you saw a number that was not real? Okay. We're going to just have Lemma 49 on screen here, which says something about the zeros of the Riemann zeta function, as you do. Okay, Trippica is going to come back. I'm going to link you to your page anyway. Everyone knows what page I'm going to link you to. So I'll put a link in chat in case you want it. The link is really fun. It's introduction to how complex numbers work, but done with lots of examples. Okay, which goes together so nicely with this. It's the real part of a complex number. Okay, what is going on then? So this is going to prove there's no zeros over here in the arcGAN diagram, imaginary part, real part, over there, no zeros. Clearly each factor is non-zero. What? It's an infinite product, so we're not sure. That infinite product could converge to zero. That's amazing. Yeah. Oh, I don't like that at all. I mean, it's true. You can multiply lots of stuff together and be left with the value being zero. But wait, we've just proved, and I sort of wasn't paying attention, but we've proved that this zeta function with the sum is the same thing as this zeta function with the product. Because the difference, mumble mumble, bound to the difference, mumble mumble, it's all okay. It's not a very noisy neighborhood, but when it's noisy, it's some very strange noises. Oh gosh, I don't know if you heard that at home, but that was like the most painful mechanical noise I've ever heard. It was either a... Well, it's still going. Right, good, okay. I can still hear it. You probably can't anymore, but I still can. Right, good. We're going to ignore that. So product less than x is non-zero for any natural number x. That's fine, because that's a finite product. But we're doing this product over all the primes. So what if we multiply these together? Oh, without the minus one, just cancel some stuff out. Multiply these things together. So look at the primes bigger than x, the large primes. And you get this 1 minus p to the minus s to the minus 1. Feels weird to carry on, right? 1 plus the sum of terms n to the minus s. Sounds like a horror film. If the stream cuts out really suddenly, if someone comes in behind me, but I'm looking at the zeta function, then you got it. Yeah, right, okay. This is my defense mechanism for horror film situations. Just Twitch chat will just let me know. Okay. Okay, what was this? So this thing's bigger than 1 because it's got 1 and some other stuff in it. Wait, why are we allowed to say this is... Why are we allowed to say this is large without saying that's... It feels like we're trying to say this thing is large, for if we just take the large primes. But this thing, ooh, we're not sure, because we're taking all the primes? Am I missing something? Yes. Oh, where n has a prime factor greater than x. Yeah, alright. Okay. Okay. So what's this? It's greater than 1/2 for large enough x. Oh gosh. Oh, it's once again because sigma's got a real part bigger than 1. So this sum converges to something sufficiently small. Don't love it. Don't love it. But, you know, take what I can get. Okay, so this thing's non-zero because you might think that the product can get really small. If you pull out this first few terms, look at the rest. The rest is 1 minus. The rest is bigger than 1 minus. Some stuff I'm not even convinced this is 1. This is 1 plus the sum of the terms. N has a prime factor greater than x. Ah, right, again, because it's... There's a geometric thing and a bunch of products and multiplying everything out again. The things that aren't 7 smooth are the things that do have a prime larger than 7. So we could make this thing smaller A smaller thing would be if we subtracted. No, why are we subtracting? Why are we subtracting? Why is there a minus sign here if we're doing 1 plus? I don't like it. Okay, we have like plus minus signs. This is the thing that's confusing me in here. But okay, I reckon I could understand that if I really thought about complex numbers for a long time. I wonder if that Trivic is coming back with some easier complex number questions for me. I need an escape. Oh my goodness. Where is this going? More complex analysis. You can extend it to get a meromorphic function. Well, it's got a simple problem, s equals 1, which is the point where 1 over n diverges. So that's fun. Here's the gamma function. I've seen it before. It generalizes factorials. You can continue that, can you? Function satisfies this. Yeah, it looks a bit like factorials. I never really like this out by one thing that's going on with it, but never mind. So this is, if you haven't seen it before, this is a function of z. So you give me your favourite number z with real part of z bigger than 0. So maybe think of a positive real number. It's like, I don't know, 3/4 or something. And this integral is something that I could work out. Maybe t to the minus 1/4, e to the minus t, and integrate that. Everything's okay. If I do that, then I get a value. Now, if you give me a whole number, I get n minus 1 factorial. If you don't, then I get something else. So it's fancy factorial. It's a way to join the dots of the factorial function. It's not the only way to join the dots on the factorial function, but it's quite a nice way to join the dots on a factorial function. Right. So for a natural number n, we have this thing. Good. Okay. Okay, so I've seen the zeta function before. I've seen gamma functions before. I've never really seen them at the same time. Now, what is this? A completed zeta function to be... Oh no. Everyone's gangster until capital psi appears. A capital psi? A capital zeta, right? No, what is that? Capital zeta is just a z. Does anyone speak Greek in chat? Yeah, it's a capital psi, which is weird. So psi is this one, and then that's a capital psi. Fancy factorial, or off by 1 factorial. What? Has anybody ever seen this completed zeta function thing before? I've never seen this. Pi to the minus s over 2, gamma of s over 2, zeta of s over 2. It's just all your favourite functions multiplied together. Like Stirling's approximation again from earlier. Somebody earlier in chat said, I don't get it. And wow, I get this. What is going on? And it's got a lovely symmetry. Is it? Good. Okay. Okay, and then... Oof. And that has a simple product s equals 1. Does it not have any issues when s is 0? Can't really believe this. Or, no, I don't really know what this means. Yeah, I really don't know what this means. How's this extending zeta? I'm very confused. Okay, anyway. So is this? No. How is this extending zeta is the thing that I also want to learn, I think. Some sort of complex analysis thing that I don't quite get right now. Does it agree with zeta of s somewhere? No. Okay, in order to prove the prime number theorem, mathematicians prove that zeta s is non-zero on the line. Real s. In fact, we know there is a 0 region for zeta in the critical strip. So it allows us to prove better error terms in the prime number theorem. Ugh, okay, right, good. I now feel like the stuff we were messing around with an hour ago, where we had all the sums of 1 over p, and we had some bounds, because maybe just zeta function stuff? Never mind. The Riemann hypothesis says that all the zeros lie down the middle. Now it's time to define a Mobius function. Oh, look, but this looks fun. This looks fun. It's the -1 to the k, if n is the product of k distinct primes. That's already fun. So 2 times 3 times 5, which is 30, is 3 distinct primes. So mu of 30 is -1 cubed. It's -1. Well, this is fun. N is not square free, if it's got a repeated prime factor in it. Horizontal Mobius function. I'm not sure it's going to tell you anything about Mobius strips, unfortunately. I think it might be the same Mobius unrelated idea. I don't know, maybe. Okay, so it's... But I've got it as something like mu of 2 is 1, because it's the product of 1 distinct prime. But then mu of 4 is 0, because it's not square free. So I don't really see how it's multiplicative. Because then mu2 would be 1 times 1. Have I misunderstood? One of those functions where there's no way you could do any maths at all with this, right? This is just a gimmick about minus signs, looking at how many distinct primes there are in your number. Yeah, I'm worried about repeated primes, right? If you're not square free, that doesn't mean your factors are. Oh no, okay, we're not going to do this. We're going to do something else. I now feel like we're on a sort of safari trip. Formula 1 on the brain. A sort of safari trip of just looking at other functions. What is going on here? Gonna look up Mobius functions, see if I can find more examples of this thing. One of its square free with an even number of prime factors, minus one of its square free with an odd number of prime factors. Mu of 2 is -1. Good. Mu of 2. Okay, what does multiplicative mean? What does multiplicative mean? What I thought? It means when to coprime. Lol. Okay, now it's easy. 2 is not coprime with 2. That's why I'm not allowed to multiply those together. Okay, now it's easy. Okay, in number theory, something I'd forgotten is that multiplicative refers to mu of A, mu of B being mu AB if A and B are coprime. Which makes it easy to prove, because coprime, they've got different prime factors, so you can concatenate them together. And if it was odd and odd, it's now even. And if it was even and odd, it's now odd. And if it had any squares in, it still does. Okay, that's really annoying. Lesson to self. Look up the definitions first before trying to prove things. Exercises are there to help you learn the definitions, I guess. The Mertens function says add these things. The trivial bound is that, right, they can't all be, they're not all 1. So when you add them, you're not just adding a load of 1s. And the Riemann hypothesis is equivalent to the assertion that the sum is actually about as large as x to the 1/2. Okay. For each epsilon bigger than 0, there is a constant such that the sum is less than. It's bounded by x to the 1/2 plus epsilon. Okay, so this is not quite saying it's of order x to the 1/2. as x grows, it okay, it's 1/2. Gosh, what's going on there? So it's like the prime factors of your number. It's not even obvious to me that it would be positive, right? Right, wow, so this says, oh no, but this says it's small. Doing the sum here. Let's have a look at some, I can see the, again, Wikipedia page I'm on has got some values of the Mobius function on here. So when I say it's not even obvious to me that the sum of these things would be positive, I'm not sure, maybe it's negative. The Dirichlet series. Oh my goodness, look at this. Wait, what? The Dirichlet series that generates this sums to 1/0. Right, okay, that's enough. That's enough of Wikipedia for a moment there. And I think finally for this section, maybe not quite finally, the number of primes grows like x over log x, which I think I've said on the Professional Thursday stream at some point, but never really looked at the proof of it. So here's the definition, by the way, of what that tilde looks like. It's sort of like a percentage error, if you like, a ratio 10:1. Elementary proofs, avoiding complex analysis, that's what we're here for. But still involving integration. Oh my goodness. The Riemann hypothesis is equivalent to, this is another thing about how people prove things, right? Somebody asked earlier, how do you have that idea? And people are trying lots of things. Evidence that people are trying lots of things. These notes are just full of things being equivalent to the Riemann hypothesis. That means that people have reshaped the problem and found other things that are equivalent. I haven't proved any of them because I haven't proved the Riemann hypothesis. But people are trying to push it in different directions. Who's to say which one of these directions would help the most with the proof of the Riemann hypothesis? Okay. Okay, so well, you're going to count the primes, where 1 prime is the indicator function. It's one if it's prime and 0 otherwise. You sometimes do a Fourier series on these. On function Safari, it's time for capital lambda von Mangold's function. For natural number, I feel like we're proving a lot less in this section and being shown a lot more functions. Log p of n is a prime power. So we've got a few of these now. We've got functions that are quite often 0, but if it's a special sort of number, then it takes some value, and this sort of picks out the interesting ones, and maybe lets you do something with those. So few prime powers that their contribution can usually be absorbed into the error time. Okay. Oh, right, there's so few prime powers, this is saying that it's a bit like... it's a bit like it's just log p once. Oh, that's mad. That's really good. It's kind of like your number's almost never a prime power other than when it's the prime itself. So the thing's basically just an indicator function of primes. So instead we're going to add those. Again, replacing a thing that we're summing with some logarithms because we're going to take a product, right? Okay. Okay, time to link zeta and lambda. Having linked pi and psi. Greek letters everywhere you look. Okay, what on earth is that? Is that the derivative? I think it might be. The derivative of the zeta function is this thing involving some logs. The sum. Okay, wait. So this is on the right. The sum where, if random chance, n is a prime power, write log p there. Otherwise 0. This is a pretty restricted sum. Don't say there's anything on the primes. Prime powers. Dirichlet series for lambda. Oh, we just saw that on Wikipedia. That was why I closed Wikipedia. Corresponding Dirichlet series. Ooh, fun. Divide yourselves by n to the s. Off you go. It's a sort of generating function, which I first saw in A-level probability or statistics or something. Oh no, it's the logarithmic derivative. It's the derivative of the log. Yeah. I should have spotted derivative upstairs, zeta function downstairs. You've seen that before. That's what you get when you differentiate log zeta. There it is. There's the log zeta. Okay, so second time today. Sums, try replacing them with log of something. For reason, we have the Euler product. Yeah, we did that. We had that way of switching out the sum for a product. There it is. Okay, so you got this thing about the log. Differentiate both sides. Oh, off you go then. Calculus. P to the minus s is this, so you can differentiate that with respect to s. Oh, nice. And then it's good. Okay, so these things are equal, and that's where you get the log p from the derivative. You know, just classically taking your p to the minus s and just differentiating that with respect to s. Ooh. You get a log p, which is the thing in the lambda von Mankel function. Good idea, I like it. So the swapping thing that we saw, we kind of skipped over it, but the swapping thing only worked for, here it is, Riemann zeta function, sum, Euler product, and this only works if the real part of s is bigger than 1. Because there's a kind of long tail in the proof to look at the effect of large numbers. I guess the easiest one to point out is the Riemann zeta function, which is adding over all n. The proof works by adding up to some amount of n and then trying to worry about the leftover stuff separately. And if s is bigger than 1 and a real number, then that tail of the function converges in just a way that it might not for other values of s. In a way, with these infinite series, sometimes you're trying to just sort of ignore the infinite tail of the sequence, and just sum the first bit. And getting away with that requires some condition on the letter s. It's in here somewhere. We looked at this very, very briefly to think about small terms, primes less than big N, and add this leftover bit, which we bounded. Eventually in here we're taking this thing goes to 0, so it's kind of leftover terms but not that big. Okay, swapping. That's how we ended up with no zeros over there on the Riemann zeta function, a proof I did not understand at all. Okay, and now I am somehow over here looking at this bit of proof, differentiating the Riemann zeta function. It's gone all right, I think. The idea is to study this along a suitable vertical line in the complex frame. I'm very excited about those. I've got one in particular I would like to ask about. One can use this to determine an explicit formula for psi. Oh no. Counting row at the same time as row bar. I don't really think I'm going to understand that. Oh no. Yeah, okay, who knows? Probably no proof or clues. The problem is then to carefully bound error terms, like I was just telling Neutrino. Oh my goodness. Number of zeros. Ugh. The number of zeros. In the dangerous bit where there might be zeros, I guess don't count the ones where there aren't any. So the imaginary part of S goes up to 0 to t. So the diagram, we are looking at this bit, counting the zeros over there. And Riemann hypothesis is that they all lie right down the middle. So just look at the middle line and count those ones. Asymptotic to find out where. Okay. Okay. Let's not. What is going on here? Everything's gone grey. I don't know why all these notes are in grey suddenly. That's usually used for little comments or notes, and here it's like loads of stuff. How many primes are there less than 123? It says here. Rule out the multiples of 2 and 3, and so on. Rule out 1, because that's not prime. Every prime factor has a prime. Every composite number has a prime factor less than root 123. P11. Yeah, there we go. Okay. Remember to count and overcount. Do inclusion, exclusion stuff for all the overcounting you've done for things like multiples of 77 or multiples of 35. Then, great. Okay. And you end up with some horrible sum. So Legendre's formula for this says that the number of primes up to x is the same as the number of primes up to root x, minus 1 plus n is the number of n between 1 and x. This sounds impossible to calculate. N not divisible by any prime up to root x. So things, okay. Things you find along the way, right? Between root x and x. I don't love this. I'm sure it's sort of reading it makes it sound too obvious. The things that you find between root x and x, right? I guess I'm counting primes, and that thing is not counting primes, it's counting n. So the thing going to be that they're not going to have any square factors of new primes in or something? No, what's going on here? Moreover, horrible stuff for n. Floor of x minus the sum of I in there. Now we're now using p subscript for the primes less than root x. Plus, you've got the repeats. Oh, right, because you might have quite a few primes in less than root x and then generate quite a lot of new stuff. And you've got to worry about that all the way up to all of the primes, just in case. Yeah, you're doing intersections here. This symbol is not a Greek letter, it's the intersection symbol, but large. It's called cap, which Gen Z also use for something else, so let's be careful. You're trying to hit the intersection of all of these sets for different primes. There's things that lie in all of these sets. Okay. And then the proof is just, yeah, okay. It's prime up to root x or not divisible by all the primes up to root x. Yep, okay. Then you find it. You test for primality of your new numbers on your new numbers. So you get that many. Good. The formula follows from that. Okay. I think that's basically what I had in mind. Finally, in this section of skim reading number theory stuff, primes between n and 2n. So I skimmed ahead to this because I really want to understand this. There's always a prime between n and 2n. It's just such a nice fact. Just this idea is that it divides the binomial coefficient down the middle. These are related to the Catalan numbers. They're great. We're going to do some bounds on these. But I think probably this is too much for the last 20 minutes of the stream. So let's have a quick look and agree that it's too much for the last 20 minutes of the stream. And then sort of wrap up gently. Primorial function. There's so many function names in bold in this. Trying to take the product of all the primes. We saw that before a couple of pages ago. So most 4 to the x. What's going on there? Okay, induction. If it holds up to n, then if n is odd, n plus 1 is not prime. So by the induction hypothesis, this thing, that thing is less than 4 to the n, yep, which is less than 4 to the n plus 1. Okay. Multiply all the primes together, and that's not going as fast as if you multiplied 4 together. Well, okay. So if n plus 1 is not prime, then you got me. The 4 to the power thing gets larger. The product of all the primes does not. This one's going to be hard. So now n is 2k for some k in the naturals. We have product of primes up to the next one. Product of primes less than k plus 1 times the... Wait, what? Look halfway down. Use the induction hypothesis down here. And what's going on here? Nothing's going on here. You've got to tell me about all this stuff. And the second half of those numbers. The product... Oh gosh, that product divides the binomial coefficient. Yeah, okay. Because all those primes appear upstairs. Yep, and not downstairs. Good. But this thing with a 2 in the front is, binomial fact, less than... Oh my goodness, look at the sum of everything. Binomial thing, some of these things, which is 4 to the k. It divides the binomial coefficient. So that's smaller than the binomial coefficient, right? Yeah, this thing is smaller than the binomial coefficient, which binomial coefficients are not that big. 4 to the k. And so this thing is smaller than 4 to the k. Okay, that's really nice. I like that a lot. I don't think I could reproduce it, but there's some really fun ideas in there. I really, really did enjoy turning the page, and wham, binomial coefficient, and they're not very big. Great stuff. Okay, so it feels a lot like finding a prime between here and there. Yeah, we want that product to be bigger than 1, which is okay. So that's kind of the opposite sort of bound to say, are there any primes in here, please? Right, alpha for the exponent of p and the prime factoration of n factorial. Ugh, okay. Yeah, this is a classic. How many times does 2 divide 100 factorial? You've got to allow for the factors of 2 and factors of 4 and factors of 8 to count as well. Oh yeah, so the classic thing is, how many zeros at the end of 100 factorial? And which is good. If you don't leave the space, it looks like you're just excited and confused about your question. The answer is 2. But 100 factorial has lots of zeros at the end because of all the 5s that turn up in the factorization here. I know that's not quite the same because that's multiples of 10 and 10 is not prime, but it's the 5s that matter. Anyway, that's a famous question. But, I use this all the time. Right, so what's going on here? So this thing is the product of all the primes between n and 2n and the product of p less than or equal to n. P to the alpha p2n minus 2 alpha pn. Oh gosh, okay. How many times does your prime appear? Yeah, how many times does your prime appear upstairs? How many times does it appear downstairs? Since this, so that, gosh, if the prime power is too large, then that thing is 0. Oof. So each someone is 0 or 1. So horrible bound. Oh no, wait, lovely. Horrible bound on J, but then this sum is fine. So prime to the alpha thing is less than 2n. So then that's good enough, right? Because that's, is that 0 or 1? No, that could be huge. Jesus, small p, do better for large p. Oh no. If p squared is bigger than 2n, then the alpha thing is 0 or 1. So split it further. T1, T2, T3, what on earth is going on? Oh no. No, this is too much for me. This is too much for me. And there's one more like lecture of more of this. Okay, bailing out, I'm bailing out. So n bigger than 100 we have, oh my goodness, look at all this. T3 is bigger than 1. T3 is something like the number of primes in that region. Ha. Amazing. That's the section. And I bailed out with at least a page to go and wasn't really following for most of the proof. One day I will try and understand this proof properly because it is so cool. Primes between n and 2n. In some sense, that's much weaker than the prime number theorem. The prime number theorem is asymptotic and tells you how many primes there are of a certain size, but doesn't guarantee that this will be true for all n. Yeah, you could be missing some of them. Yeah. Sometimes it has to be true sometimes that you get a prime between n and 2n, because there's infinitely many primes. And I think the prime number theorem tells you that it happens. I'll try to link it because prime number theorem says that the asymptotic density is 1 over log n, which doesn't help. Okay, there's some link back to how the prime number theorem gives you this intuition that there are actually quite a lot of primes between n and 2n, but it's not, because of the asymptotics, I think, not an actual proof that there's one between n and 2n for all n. So this is worth knowing, I think. My takeaway from first looking at it is, my word, it's hard to prove that there's a prime between n and 2n. And apparently, so this is Bertrand's postulate, proof, an elementary proof. The thing that these lecture notes said a few pages ago, several pages ago, was that you can do this with complex analysis. But this is an elementary proof. Is that what they said about this, or is that what they said about something else? Maybe they said that was something else. Okay, I think I'm wrapping up because I'm not understanding things anymore, and I fried my brain by trying to follow inequalities, so many logarithms, and products of prime numbers. To be honest, I should probably have given up when the complex analysis came in, because this is not really a complex analysis stream. But hey, got to see some cool stuff. Yeah, we're going for an oh no. I overloaded this, and I've still got to do all my marking. We're going to have, does anyone want to ask maths questions or do anything else? Otherwise, I think I'm going to stop a little bit early. I think I might stop. We'll just get back and understand one thing. Let's try and finish on a high. Mary's giving me oh no, which is a sad note to end on. I'm going to retreat to the safety of quadratic forms. Yeah, lemma 37. Yeah, cool. Phew. Okay, safety. 1 + 1 is 2. Welcome to Chill Maths, broadcasting live on Twitch. Right, safety of lemma 37. Let's have a read. Okay, n is properly represented by a form that's something in the form ax squared plus bxy plus cy squared. Can you make n? Properly represented means, can you make n with coprime x and y? If and only if f is equivalent to a form. So equivalent means that you can rewrite this. You can sort of complete the square or collect the terms together to make a different form with different coefficients. That completing the square thing, there's a nice way to write it with matrices and matrix transposes. The matrices look a bit like that. We will get there in a second. Okay, I want to understand what that's got to do with a form with first coefficient n. If f is equivalent to f prime, then f prime of 1, 0 is n. Yeah, okay, fine. If it's equivalent to this, then you can stick in 1 and 0 and you will get n. The other way around. If you can make n, can you prove that those things are related? It's more chill if I can't do it. Yeah, that sounds true. So Bazoo tells me that I can make integers like this. I believe that because I've seen how to do Bazoo from Euclid's algorithm. So then, okay. So this is going to be this matrix has determinant 1, xs minus qy is 1. It's the determinant. That's the thing that you build with Bazoo. Bazoo also lets me generate things with a plus sign in. That's a stupid observation because I'm allowed to take negative numbers for Q. Good. So F is equivalent to F prime. Here's the matrix that you use on that. Now, do I understand why that matrix actually works as the transformation between them? Not really. F is equivalent to a form F prime with F prime of 1, 0. Oh gosh, F prime of 1, 0 is then the same thing as F of xy. F prime of 1, 0. So if this can make n, where x and y coprime, then you can take your coprime x and y and rewrite them, or rewrite some combination thing. So you've got your coprime x and y, and then you can do something like this. What's this going to be? You do something like, you can rewrite this as xs minus qy squared. Oh, what are we trying to do here? Yeah, that's not quite the transformation. How does that transform? What's my actual transformation I'm supposed to write down? Oh, am I doing it to the ABCs? Yeah, I think I'm doing it to the ABCs. So I'm doing it to the A, B over 2, B over 2, C, kind of matrix representation for that form. I'm supposed to apply my matrix like this. XS, YQ, like this, but you put the transpose over here. If I multiply that out, I get a really messy quadratic form, but this quadratic form, once I've multiplied it out, if I plug in 1, 0 to this form for the values of, no, not quite. If I plug in 1, 0, I'll get the xy, I'll get n. If I put in 0, 1 and 0, I'll get n. So it has first coefficient n. XS, that's mad. So if I multiply it out, then I'll get things like x squared plus bxy plus cy squared. I can sort of see that. Yeah, it's crazy, but I'll get things like that. That's one of the coefficients. That's actually equal to n though. So when you throw in 1, 0, you actually get n back. So the matrix multiplication actually works out. I suppose the matrix multiplication has to work out because that's what putting xy in is. And then QS gives me a way to complete that into a matrix. So this has got determinant 1 and lets me generate these other coefficients. So it's not quite like completing the square then, but it's all multiplying out. Okay. Let's go with the term. What's the determinant going on here? Discriminant thing, right? So then there's a bunch of maths down here about discriminants, because it's a bit suspicious that you get to something with an n. B squared minus 4nc has to be minus 3 because that carries over 1 squared minus 4 times 1 times 1 is minus 3. Okay, so can you get a solution like NBC? Okay, I'm going to 5 minutes of trying to read all this grey text, and then I'm going to call it a day. If we know there's a solution, then there are integers such that this is true, so that NBC is a form with discriminant minus 3. B squared minus 4nc would be minus 3. But we don't know that that's the same as 1, 1, but reduced forms, mumble, 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 only reduced form, it's 1, 1, 1. So every positive definite form is discriminant minus 3 is equivalent to 1, 1, 1. And there's a form of that, like that, if and only if there's a solution to w squared is minus 3 mod 4n, so that you can make the discriminant, so that you can choose what to put for b to make the discriminant equal to minus 3, and then it'll be equivalent to 1, 1, 1. So the form MBC looks like this, if and only if there's a solution to this quadratic residue question. Mod 4n, independent of c, that's the kind of multiple of 4n. And it'll wind up being equivalent to this. It'll have the right discriminant, and we know that A form. This says something like A form. Then it's represented by A form F. If and only if it's equivalent to A form. Hang on, that one is by the form F, I think. If and only F is equivalent to A form with first coefficient n. So MC is equivalent to, we don't know that those are related. Okay, these forms are tricky. And then there's theorem 38 here. Suppose that n is properly represented by a form of discriminant d. Then there's a solution to that congruence for any discriminant, not just minus 3. Then there's a solution to that. So f is equivalent to one of these MBC things. And b prime is e prime, fine. And that gives you your solution. B squared is d mod 4n. B is your solution. Do you need primes here? I think they want primes. I could put some primes on here. Oh, d prime is the same as d. I'm an idiot. Yeah, I think it's b prime. I think I want b prime in here. Suppose there is a solution, then there are integers such that b squared is 4 plus d plus 4nc, so then MBC is such a form, and then probably represents n. Okay, right, final bit. It's labelled the main thing. Trying to push through to understand what's going on. Can this represent n? It's the same thing. It's a solution to this, and if there's a solution to the congruence n, it's properly represented by some form of discriminant minus 4. B squared is 0, minus 4ac is minus 4. What are the reduced forms of minus 4? Only 101. So theorem 38 tells us that n is properly represented by 101 if and only if there's a solution to b squared is minus 4 mod 4n. And then dividing by 4. This happens if and only if there's a solution to b squared is minus 1 mod n. So that link is weird. There's a dividing by 2 thing going on here. W squared has to be even, and then divide by 4 on both sides. That's subtle. Equivalent to some form. So if x squared plus y squared could be some number n, if n's the sum of 2 squares, then there's a form with discriminant minus 4 with first term n. So b squared minus 4n would be minus 4. So b squared will be minus 4 mod 4n. So it's even, then you get b squared is minus 1 mod n, which is like saying that n is a factor of v squared plus 1, which is like, okay. So properly represented means x and y co-prime, which is necessary for me to build this relationship between the forms. Okay, think I'm getting there a tiny bit. If and only if there's a solution to minus 1 being a square root mod, minus 1 being a square number mod n, which is so cool. We now know that happens happens for 2 but not 4. It happens for primes that are 1 mod 4 but not 3 mod 4, and then powers of those primes happens as well by that thing called Hensel's lemma. And it works for products of all the things I've mentioned so far. So separately. Wait, is this? So it's n squared. No, yeah, this is not related to. There's a lovely thing about products. For the 2 squares problem, there's a kind of product fact where you can think about the magnitude of the product of 2 complex numbers, and that gives you the product of the sum of 2 squares. Sum of 2 squares for each of the complex numbers, and you multiply them, then their product behaves. The magnitude of their product behaves nicely. Okay, fast stream. I learnt that I don't remember as much complex analysis as I thought, and maybe my resolution for this year to learn more integration should include complex analysis. We saw some pretty scary number theory, but then retreated back home to try and understand quadratic forms and which numbers can be written as the sum of 2 squares. I'm going to call it there because it's 4 o'clock. Thanks for watching. Thanks for following. If people joined, a couple of people joined the show today. I'll be back on Thursday on my professional stream for work. Not with Matt Parker next week. That was a one-off thing. And we'll be doing something like this on Sunday, probably next week, I think. Yeah, probably next week. Do something like this on a Sunday. Maybe not number theory. Maybe number 3. Maybe not number 3. Something else. Might have seen too much number theory for a while. Okay. Right. Take care, everyone. Have a good week. Mountain Snatch understood a small amount. Hooray! We saw some new things. We tried some new things. Pushed maybe a little bit too far into Vermodl's function, but we try our best. Right. Okay. Keep learning. Good luck, everyone who's learning stuff, wherever you're learning it and whatever you're learning. Bye.